All right, so welcome everybody. So I will give brief introduction to theory of single electron semiconductor quantum devices, and I will talk about quantum entanglement and decoherence in systems of electrostatically interacting semiconductor Wannier qubits. So let me briefly describe this current status of quantum technologies and define the target of my research. So basically, among all existing technologies, I believe that quantum dots, especially semiconductor quantum dots, is one central feature of being very scalable, and this feature allows to make very tiny devices, and this is especially important when we deal with the most recent CMOS technology. So, as you know, the transistor length and transistor size becomes smaller and smaller. So right now we do have like 7 nanometers length of transistor between source and drain, and this keeps to be downscaled further. So that's why we can approach quantumness from the perspective of semiconductor silicon devices that is an alternative towards commonly used transmon superconducting qubit as represented by IBM quantum experience. We can do various devices based on that. So we can design quantum neural networks. We can design hybrid interfaces like classical quantum algorithm, and also think about classical quantum algorithms as well. So all can be embedded in a cryogenic environment. Okay, so I will not go into details of those technologies, but somehow semiconductors are behind superconductors in terms of coherence time. So they don't represent high coherence time. Nevertheless, this issue is still under development. So here is the sketch of the scheme of the concept how to functionalize commonly available commercial CMOS device. We have a source and drain, and the source you can inject electron to a source, so to region 1, and so this is like effectively quantum dot A, and then you have region 2, so this is like quantum dot B, and then the electron can tunnel from left to right side. So this is this system of transistor can be equivalent to systems of coupled quantum dots. So you can develop this further by having two transistors in parallel, or quantum devices in parallel. So in that case, there is occurrence of electrostatic Coulomb force. So there is an anti-correlation principle in place, as you can see here. So you can go even further into construction of interface between a semiconductor quantum dot system as placed below, and Josephson junction, which is a superconductor, non-superconductor system. In such case, you can use the movement of electron among two quantum dots as a source of vector potential that imprints on Josephson junction phase difference, which you can detect by IV characteristics, and also you can see the modification of underground state due to presence of quantum dot systems that are nearby. So using such type of scheme, you can create two types of interfaces, like inductive interface. So here you close semiconductor loop, and you inject single electrons inside, and this is coupled to superconducting quantum loop with Josephson junction. So this is like flux superconducting qubit. So we can have the interface which is inductive between two types of quantum electronics, and you can have interface that is based on electrostatic interaction. So there is semiconductor nanowire, and this is in parallel to superconducting here Cooper pair box. So the electrostatic principle is used for interaction between those two types of quantum systems. So you can do such type of devices and networks. In particular, you can entangle two qubits via distance using superconducting resonance cavity, and then then you can use so-called tight binding model, and then there's entanglement between a position-based qubit, which is given here, and resonant cavity. The position term is because you can encode quantum information by linear superposition of eigenenergy functions, as it is done in kind of common way, or you can do it by assigning the presence of electron left side to probability to one logical state, and the probability of occurrence in another area to another probability. So that's why we call it Wannier qubit. So here's the scheme of quantum neural networks. So this is essentially we inject electrons to chain of quantum dots, and then there are gates on the top, as you can see here, and this wave packets propagate, and the result of this propagation is, so basically that's issue connected to the quantum transport in those structures. So you can then come with different methods of its modeling and searching for different types of interactions. In this framework, we do have a programmable quantum graphs. So since we can control connectivity between two areas electrostatically by setting certain voltage in between, so we can build barrier or release this barrier depending on the situation. So that there are the possibilities, and we can do so close. We can have a closed Wannier qubits as defined here. So this is roton Wannier qubit. So electron is rotating on the closed circle or closed area, and then it can be both controlled by electric field and by magnetic field, as indicated over here. And then there's a question: what is the model and how to approach this decoherence modeling? So at first, this is standard qubit, which you can see. Standard wave function is nothing else as superposition of eigenenergies of wave functions corresponding to each of the eigenenergy. And then you have like standard Schrodinger equation. Nevertheless, you can think on the system in slightly different way. You can say that let us consider now the case of two coupled quantum dots. So we have a occupancy of eigenenergy A1 and A2. We presume it to take place, and then what we know is that occupancy of left and right will be time dependent. So we can make a kind of rotation of this wave function spinor of eigenenergy spinor, and then we end up in Wannier wave function left and right, which is indicated here at this formula, and basically we can control the angle in such a way that the left Wannier function is maximally localized on the left, and then right wave function is maximally localized on the right. So in such a way, you move your kind of qubit information from eigenenergy space to Wannier space, in a sense, to Wannier wave functions space. So that's a prescription that is given here. And now how to model the systems? Well, we do have a slightly described over here. So we have a Hamiltonian in a spectral representation. So this is most minimalistic model you can imagine. Then you can encode all electromagnetic situation by such matrix acting on a eigenenergy spinor, and then you have time evolution, right? So this is from, you can move from eigenenergy kind of representation that is denoted by formula 5 into formula number 6. And how you do it? You just put rotation matrix as identity in certain places. So here it's sketched over here, and finally you can arrive to such prescription as formula given by number 7. So what you have is you have eigenenergy, you have energy matrix or Hamiltonian representation, energy base, and then it's rotated by angles into the opposite directions on left and right, and then you end up in so-called tight binding model. So here we have AP1 and AP2, so those are about energy localized on the left and right quantum dot, and there's a Hoping constant TS12 that's on matrix and anti-diagonal. And also at the same time, you do have a prescription for Wannier wave functions. So it's given by formula 8. So you see this is linear combination of two eigenenergies. Two eigenenergy wave functions. Of course, it can be more than two, but this is kind of more minimalistic. And then you have also all the properties of orthonormal Wannier base that's specified on the last line that you can see. And then you can search for this exact value. So then you ask what is the value of theta, and there is in case of one-dimensional qubit, where you separate left side as occupancy from -infinity to 0, and then you have right side. Then you have such formulas given by 10. So this is such kind of ratio. So, and this doesn't depend much on the curvature of the cable or even dimensionality of the cable. Nevertheless, in case of 2 or 3 dimensions, you need to take into account more like integration around the x and z. So that's quite general formula. And then we see how the diagonal terms are dependent on eigenenergies and this theta angle, it's given over here, and how Hoping terms are dependent. So that's how it is. And the same scheme can be repeated in many types of system. So here is the case of two interacting single electron lines. So the most minimalistic system consists of base of 4 Wannier wave functions. So all the 4 combinations of localization on left up, left down, quantum dot, and so on, so on. So let's say in regions 1 and 2. So this equation 12 corresponds to electron presence in upper line between 1 and 2 region, and lower line 1 prime and 2 prime. So this is kind of such most minimalistic system. And then again, you have two-body tight binding model that you can derive from a perturbative Coulomb interaction and with usage of Schrödinger or Dirac equation. So that's how it is. And then there is this prescription for these terms. Then you have a Coulomb diagonal terms. The problem is that actually what is real source of decoherence over here is actually that if you start 2 qubits to be in 2 energy occupancies, so one occupies 2 eigenenergies, and the second is also occupying 2 eigenenergies. If they quickly interact, then what happens is that this Coulomb interaction will warm them up. So there is non-zero probability of going to higher energy than occupancy of 2 energies. So after long evolution time, the state will decohere. That's how it is. Nevertheless, it's good still to start from simplistic model as I specified before. So here's the whole methodology of modeling these devices, and the whole methodology of let's say of dealing with a quantum entanglement. I'm not top. So the essential idea is that if you have perturbative interaction in eigenenergy space using energetic picture, the level of entanglement is quite minimalistic. Nevertheless, it can considerably increase if you move from energy-based to Wannier-based. Then you can really spot it. And here is the prescription how to describe the ground state for weakly interacting system, how to minimize this eigen energy, the ground state. So you can get its evaluation over here. So here, what has been already conducted was full validation of usage of tight binding model for any type of electromagnetic situation. And that's quite essential, because what we want to do, we want to create a kind of cascade for single electron devices in semiconductors. So that's our purpose. So that's why this tight binding model needs to be deeper resolved under many circumstances, also on body system circumstances. So here is also trial of usage combined Bogusov-Dijon equations that stands for Josephson junction, and in combination with electrostatic interaction with single electron devices. So here we also try to move the whole picture to kind of Wannier base for this hybrid system. So that's what we do, and then we end up in such type of Hamiltonian, and that's essentially. So we see that doesn't change. This structure of Bigov-Dijen equations is preserved as specified over here, and then we end up with such kind of model for this two system interaction. So that's quite essential to know it and to exploit this properly. So we also are capable of doing modeling these various types of devices like banded curves of nanowires, and all this tight binding model works quite well for them. So what happens here is that actually bending the cable results in a kind of like dissipative factor. It shouldn't be surprising for you, because if you have movement of ball in curved tunnel, it does slow down because walls just are kind of slowing or speeding it up at some point. So that's why this presence of a kind of term proportional to a kind of momentum takes place in a kind of Schrodinger equation, which can also be treated as a kind of decoherence. So we can find this various solutions for such type of system. So basically, we have spotted topologically protected qubits in this interface between a Josephson junction and a quantum dot system. So we can generalize it further. There is semiconductor quantum swap gate over here. So that you can have a kind of like NOT gate by using two parallel coupled quantum dots, and this can be in parallel to Josephson junction system. So that's the general scheme of creating this hybrid superconducting semiconductor quantum computer scheme. Again, we do have a kind of tight binding model, and then we can solve it analytically. So let's say if this is 4x4, everything can be solved analytically at higher order then we are pushed towards numerics. So we spot various types of solutions. So we have the eigenenergies versus distance, and superconducting order parameter versus eigenenergies. So what is quite remarkable in some of those pictures is that ground state can exchange its role with excited state. So this is indications of quantum phase transition. So that's quite prominent observation, because it can push those hybrid systems to be a good candidate for a kind of topological qubits. Yeah, so you can spot various features of the system. Perhaps I will move quicker, and then we have shown. So we have shown topological phase transition and protected states and so on. So let me move further to this description of this decoherence term. So basically, the idea is that if you this is spectral representation of a Hamiltonian, and there is non-zero. So let's say, I would say maybe in a different way, that it's quite famous known work how to ionize the atom of hydrogen using microwave field. So even if you use a very small time-dependent electric field, then there is non-zero probability of kicking the system from energy from first electron from first shell to infinity. Nevertheless, this probability is quite small. So that's how it is. So basically, this full description of two-body interaction consists of infinite matrix in this kind of energy spinor representation, and then this decoherence intensifies with time. So that's how it is. So we try to find schemes that account for such type of effects. So here is just example how to evaluate certain terms of Hamiltonian in this perturbative approach. Of course, when you deal with non-perturbative approach, you have to solve things more rigorously. That is not yet in the scope of currently conducted work. And then also at the very end, I would like to share very phenomenological roton-roton interaction problem. So since two-roton system is like two-roton system, so what I call it, it's like you have a circle semiconductor on a wire that is close to the circle, and then you force those two circles to interact by kind of inductive, by kind of electrostatic interaction. So you can pre-assume that there are two balls. If you can see the system classically, there are two balls moving on each of the circles. They correspond to eigenenergy E1 and E2, and then what happens is that this probabilities occupancy with time that does depend, but all other quantities are fixed, and then you have this probability of interaction of the ball from angle phi1a, so first energy level of a qubit, with another ball, charged ball, that's electron phi1b. So in that you can construct such mechanical energy quantity, and of course, you know, this is it's preserved. You can pressure the dynamics of this angles with time, having the constant angular velocities corresponding to quantized eigenenergy levels, and then you can observe the evolution of this probability of occupancy of first and second Rotom qubit with time. I think this is kind of novel model that is semi-classical, that is still under development and evaluation, and we are just further testing this in detail. All right, so that is all for today. So I'm open towards your question and remarks. Thank you.
So thank you very much. Let's thank our speaker. And now we have time for questions. Oh, okay, maybe Mike is first, and after that.
Are you working with Dr. Kordiak of KAU?
I'm sorry, could you
Dr. Kordiak, is he working with Dr. Kordiak? Because what I'm curious about is Dr. Kordiak was mentioning novel geometries for Josephson junctions. And I'm wondering if he's in contact with him, because that might be interesting for this qubit.
Kordiak, could you type his name on the chat? I would appreciate that. I can just.
Yeah, we cannot now type because yeah. But yeah. Mike, after that, Mike can maybe chat, because we are here in audience. It's difficult. Okay, another question. So, but please here, because we have.
Okay. You considered a very complicated system of qubits with electrostatic interaction. So my question is, what you can say about the role of Coulomb interaction and electrostatic interaction in the decoherence processes? So what about, for example, Anderson orthogonality catastrophe or something like that? Going from probably quantum wires connected to the system, or so similar effects. So what you can say about that?
Well, I would say that essentially, it's a kind of stage of design. So let's say if you have a transmon qubit, superconducting qubit, well, it's quite remarkable that you use both electric and magnetic field to control it, right? So somehow this scheme of mixed control by two types of fields, electric and magnetic, seems to be quite effective. And I would expect that electric field control is not enough for having very good semiconductor qubit. So I would rather go into such mixed scheme in general. So there is a big charge noise in case of single electron devices that needs to be coupled, that needs to be tackled very well. So I would rather go into, you know, the interaction with microwave field and so there are ways to think about topological protection of qubit in case of semiconductor quantum dots.
Okay, thank you very much. Oh, okay, one more.
In other words, what is the main source of decoherence in your system?
Charge noise. T2 time is very short. Charge noise. So phase imprint. So in general, experimentally, charge noise is seen here, and also it does depend, because you can have the same let's say chip, but you utilize the same chip for representation of quantum information by means of you know, the superpositions of eigenenergy wave functions, or you can do it by superposition of Wannier functions. So you have two possible schemes. So I would say that that Wannier approach seems to be more promising for the case of systems with high level of logical density. That's my kind of belief, but still I need to prove it deeper by simulation and by experiment.
Can it be said that so what you called charge noise is just fluctuation of quantum fluctuation of Coulomb interaction in the system? Can it be?
This could be like that, but I think that not all sources of noise are fully resolved, even theoretically, in case of semiconductor quantum dots. And yeah, I would say, okay, so the thing is that first approach to quantum information processing was in 2003. Fujisawa and Peta, they have implemented single electrode devices for the first time in the world. And there was a lot of people went in this direction, but then they discovered this charge noise, this noise problem, and then people after De Vincenzo criteria, they turn towards spins as the best way to encode quantum information, and somehow till now this is dominant direction of research because like transmon is nothing else as a kind of pseudo spin base in a way. So you have circulating current on the closed loop. So this is like spin up or spin down. So let's say, but because of novelties in semiconductor industry and very advanced development of lithography and the sizes of structures become smaller and smaller, the Intel, Google, and many other companies starts turn to semiconductors as one more time as a kind of mainstream for possible encoding qubits. So that's, I mean, technological development drives me towards studying this direction, I would say, even theoretically further. So I believe that that's supposed to be, because semiconductors, at least semiconductor industry is more interested in semiconductors than superconductors. So somehow this, I would say that more research towards semiconductor quantum chips supposed to be done.
Okay, thank you very much.